Good afternoon. It's really a great pleasure to introduce Moira Chas. She is giving a frontier lecture in mathematics, which is a series of lectures of excellent mathematicians talking about very contemporary aspects of mathematics. And Moira, not only being an excellent mathematician, she's a specialist in non-dimensional topology, she also has the talent to be able to explain things in the way that people will understand. And I'm sure that she will also give you the feelings of the beauty of mathematics. Because usually, you know, we mathematicians, we see beauty in mathematics, but other people do not see it, usually. But after you listen to her, you will see that you see very much the beauty of mathematics. Moira is an international mathematician. She has the background in Argentina, in Spain, and in the United States. And I think to have this WIMSA lecture today is extremely symbolizing the month of March, which has two important days that are relevant. So March 14 is International Day of Mathematics, the Pi Day. That's how it was announced by UNESCO. And March 8 is the International Day of Women. So we're celebrating the Frontier Lecture, WIMSA, March 8 and March 14. So the floor is yours.
Oh, wait. Can you hear me? Yeah. Okay. So, gosh, somebody said, Jacqueline said, shouldn't create very high expectations because then you can only go low. Thank you for that presentation, but it scares me a little. Anyways, I'll do my best, which is the only thing I can do. And let me start. I'm going to start with a question. What is this? What is this? Anybody know? You can yell it. Oh, you don't talk, we're going to go very bad in your response. Mathematically. Yell. Anybody think it's a Möbius band? Okay, good. And why do you think, no mathematician, do you think this is a Möbius band? Maybe you don't know what a Möbius band is. What do you think? I don't know, it's a perfectly good answer, which, we should learn mathematicians.
I'm going to go to the chat.
Well, you heard this lecture, so don't. Yeah, I have the same question. This is really embarrassing. This is what we do, We want to look so smart. Anyway, so, well, I'm not sure you know what a Möbius band is, but for all of you, math people do know, but let me just tell you one very first way, fun way to think what is a Möbius band. So, first approximation is we start with a rectangle. And what we can do, just if we will feel like this, one thing we can do is glue these two edges. We do this, what we get is a cylinder, a hollow cylinder. And you say, well, maybe it's not exactly a cylinder, it's a formable. But I'm thinking about shapes up to the formation. So it's a cylinder-ish. Now, if I do one turn and I glue it, I get something which is called a Möbius band or Möbius strip. It's different from the cylinder. And it has a very special property that I'm going to discuss in a little bit. And notice what happens with my shape, the shape I was showing you. It has colors. The colors are intentional. So you see a brown and a yellow. Well, I can't create that by the procedure I described because the brown is only one side, and the yellow is another side. So I will never be able, if I start with, I project these things, this one is yellow on one side and blue on the other. If I do one twist, the yellow and the blue are going to clash, are going to be together. So this is a Möbius band. Now, I could twist more. If I twist twice, I will get blue and blue, and that's no longer a Möbius band. If I 3 times, again, it's, so that's the properties of Möbius band that we're going to talk about. This thing, then this one, which is the same as this one, and I'm going to pass them so you can see, it's not a Möbius band, but it looks like one. And sometimes, we tend to, mathematicians, when we see the image and we answer that, and the question is, well, just look at it and pass it, or don't look at it, but okay. Okay, so now, wait, I lost my pointer here. So this is not a Möbius band. And here, this is a game of Pac-Man. And this particular game of Pac-Man has the property that if you leave the rectangle of one of the vertical sides, you enter exactly at the same spot on the other vertical side. So you could be playing this game in a computer, but really the space where the Mr. Pac-Man moves is the cylinder. So here we have, we know our gut, if you play enough the game, even if you don't have visually a cylinder, it will work as that, and your mind knows. So this is a lot of what we do in mathematics. We play Pac-Man a lot, or Pac-Man-like things, and then we swallow, we just try to get the intuition of whatever space it is by their property, by some special thing. So here I'm putting a map. This is a map in the cartography sense. A map of the earth, a map of the country is not the country. It's some kind of thing that we associate with the country that makes you visualize certain aspects of the country. So here, this is what I call a map of the cylinder. And we're going to have some maps of, other shapes soon. So here I have the Möbius tree band, and, we have to glue the 2 edges. When there's an arrow, means you have to glue the 2 edges, making the arrows match. And I say glue, but you have to think more of a tiny zipper invincible that you zip, disappear. It's a property, it's a mathematical thing that 2 points become 1, like magically. So, what do we care so much about Möbius bands or Möbius trees? Here we have a wonderful painting of Escher, and you see you have there ants. And what happens, the property is, I lost my Möbius band, just in this. The interesting property that you probably have seen, but I'm going to do it anyway, is like if I start walking, I start at a point here, and I'm going to walk, and I ended up at the same point, but pointing in the opposite way. I started here, I ended here. I mean, imagine what it is. It's like, I just get rid of this talk, I get bored, and I leave this room, and then maybe I come back, and I'm walking underneath in the basement on the ceiling. This is the property. Of course, gravity, there's a lot of things on my way to do that, but this is the space that we're talking about. I mean, I'm looking at from your side, imagine yourself there, gives you another way of understanding things. Another way of thinking of this line bubble is here, well, you have all these arrows and pointing out, and you cannot put a set of arrows all around pointing out without having a crack. Some pointing out this, pointing out and not pointing out. So now it's a little history. The first time that we know of, the Möbius band appeared in a publication, was a publication not by Möbius, but by listing another German mathematician. And I pointed out, he put the picture there, and he just said, oh, look, here is the Möbius band. Look, it is the Kirchhoff band. Here is this shape. Just an example of something. And later, also Möbius published the description of the band. For some reason, it stayed with his name. Maybe because Möbius was really interested about thinking about the properties. He looked at this space in his own right. Yeah, there's a little more of Möbius. These are the nodes. This is not primitive node. This is his node and this is his picture. And here you see he was exploring shapes made of triangles and triangles loose in certain way. And then he said, oh, look, and then he studied the number of twists and he draw, study what happens, what I mentioned at the beginning, how many twists, gives you which space. And here is an interesting fact about the Möbius band that these two mathematicians, Klein and Möbius, they both talk with a great, fantastic mathematician named Gauss. Gauss was one of these incredible visionaries. Gauss, there's both mathematicians in their work mention a very unusual surface. If you see here, let's see, can I point? No, let me check. No, I can't point. I point here. You see my pointer? Oh yeah. No, well, anyway. That little cross you see there, if I glue opposite edges, it takes a little time, but you get a certain shape, and it's the same shape that Listy draw. So there's a very unusual shape. In fact, I have this is a shape that appeared in the paper of these two mathematicians. It was very unusual for its time, and that may suspect that maybe it was Gauss. Now, and one more detail is that Gauss, Möbius said, Gauss mentioned this surface to me. He's the one who mentioned. So maybe it was Gauss who invented the Möbius band. It is possible because Gauss has this very visionary mind. And an interesting thing about this shape that is hard to see at the beginning is that, well, you see, this one has two colors. Again, I made all this work to crochet into colors, and there's not a Möbius band in this surface, meaning that if I start working on the purple side, I will never go to the orange side. It has two sides, spatial mathematical property. And it has, this is called a boundary, it's like a hole. Now I'm going to close the hole. Imagine that it is perfectly closed, all orange. And this is like the surface of a bagel now. A little fat bagel, the baker was a little drunk when he made it or something, but so this is the surface that was, now you can press this and keep going. So here is the story, and okay, and this is already what. So joke. Why did the chicken cross the Möbius strip? To get to the same height, because there's only one. So I'm going to show you now, light blue. This is another surface, another of these places that I'm thinking. It's in two colors, and they have a reason. And I have here another version of that surface. And what is this surface? Well, if you look at it, this circle here, hopefully you can see it, this is the boundary. There's a circle that has one boundary. Let me just mention one thing that I forgot, important. This is, remember our Möbius band, it has only one boundary, meaning that if I start with my finger and I go around and around and around and around and go around the edge, you can probably follow it, and I'm not sure I did it correctly, but you can do it in the Möbius bands that are floating in the room. If you do that, you go across the whole edge without lifting your finger. So in the spirit of thinking, there's two circles of the fourth circle. Here, there's only one. And maybe I'm giving it away, but here we have also only one edge. And you should try it. I'm going to practice around. If I start working here, and I'm going to go around, 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 I'm not touching the edge. I'm going in and in and in, up. I enter on the other side. So this thing has a Möbius band inside. Well, the thing is, it's a Möbius band. look at it. And, and here is a question. This is for the non-mathematicians, Look at how I phrase my question. What do you mean by a Möbius band? Of course, if I say, for a Möbius band, you grab a ridge over temporal and you twist it, this circle thing is not a Möbius band. But I'm always thinking of surface up to the formation. And as a mathematician, we give a lot of very precise meaning to words. And sometimes it takes a long time to really swallow that meaning and understand it with your gut. But then when I give you this precise definition of a Möbius band, and I could convince you that this is a Möbius band, I have a way. So here, when I glue it, I should glue with a piece of paper. I start with a piece of paper that has two colors to visualize certain things. The two colors, they have to clash. And I said paper, but you should imagine of a very, flexible material that you can stretch. I don't like to break, but I can stretch it and deform it as much as I can. And now I have a video. This Möbius band, I knew somebody said, oh, there's a Möbius band that has its boundary on a circle. And it's so strange that statement. I've seen Möbius bands all my life. And you have to deform this, something like this, so that the boundary is all in a flat circle. It's hard, and I tried to make it and remake it and think. And finally understood it, and then I found this video that I wish I had seen before, because it shows you how can you deform the standard Möbius band into that. Sorry, I'm going to borrow my thing. Good, here's just checking into this. Easy to me. I look at it, and Mina mentioned about beauty, but I think, well, I like the beauty, and there's many beautiful objects you can construct following mathematics, but there's the beauty of understanding something. When you clicks in your mind, and as I said, requires work, but it's fantastic when one gets it. Okay, now I'm going to do a little bit of shameful propaganda. So this is the window of the hotel. We're in a really nice hotel, pieces, and you can see the water. I love the view. And this is what we have, a painting that we have on the other side of the window. You see the window reflected there. Now, if you're a woman like me, it's very disturbing to see that. It's maybe we don't notice, but it's really a message that we constantly get. The message, is like, well, we are objects, we are things that we no mind, no face, we're just there, to what. So, I think this is part of the reason why we have very few women in mathematics. There's a society, we are not teaching, women that you have the brain that could do math. And it starts very early. A cute little girl there is my daughter. And she came once from second grade and said, boys are better than girls at math. And I felt like she rubbed my knife and put it in my heart. It was awful to hear that. And of course, we didn't teach her that, but she learned it at school. And then this is the objective mother talking, very objective. She was great at math, she loved it, but since that second grade, she went far and far away from math. So I don't know how to solve this problem, but I think awareness is a good thing. So don't treat women like things in that painting piece. Okay, so now here is the Klein model I'm going to talk about. And again, let's see that is going really fast. So let's keep that in mind, that we are going to build spaces that maybe do not have physical existence. We're going to build spaces from maps. So Klein, which is the mathematician the father is named after, he says, Normally, there are certain surfaces, if you wrote in German, but obviously I'm translating, certain surfaces, the one-sided surfaces, or one-sided, one color, with no boundaries, and he said an idea of this might be formed does not say this is really the space, it's that we can get an idea of these things if we have a tube and we glue it and you have to pass through it stuff. Now, we are talking about surfaces. A surface in math is a space where if you are a tiny insect standing at a point of the space, what you see is the plane. And the same way that the Earth looks flat to us because we are very small with respect to the Earth, these are other spaces. Maybe they have the shape of a donut. But the thing is, if you're standing in a little spot, you cannot see the whole thing. You just see a little bit around you, it looks flat. So, of course, looks flat means that it cannot cross itself. Klein describes something that crosses itself. But the point is, if we want to visualize the surface in our space, which is 3 dimensions, we cannot build it without making it cross itself. So now we have to really use the idea of math because we cannot make the whole thing, and I'll go a little more over this. So here is how to construct the instructions that you have to make the arrows match. And if you want to make the arrows match with the direction, well, there's no way to do it without crossing itself. And I'm going to skip because I'm being very slow. So here, what I'm showing there is a map of the Klein bottle. I think this is a map in the cartographic sense, a map that tells you how to construct the Klein bottle. And the idea is, well, he said, Klein said, start with a tube. Here, zipper is a little bit, well, I'm not going to a zip because I'll tell you, this is a rectangle. I zip it, and now I have these 2 red zippers there in the opposite direction. So if I try to zip it, and you could, you're welcome to try, well, you're going to get something very crumbled. With a zipper, but you can't close it because it's in the opposite direction, so it will do something bad. So well, what can we do? Zipper and zip and check to make it with again. But ideally, in our mind, we can construct this space. We are playing Pac-Man. Have you ever played Pac-Man, any of you? Yeah. So, but now the rules are slightly different. So, if you go out on the side on the red, on the vertical lines, if you go out, you come out on the same exact height. But if you come out in here in the blue, if you go in the horizontal lines, you're going to go in the opposite way. So, your mind, in fact, you can play like if you're interested, I can tell you how to play Pac-Man with this type of thing, Pac-Man or some game. And I do have an 4:45. Oh, God. I thought I started 3:30 and I was panicking for time. I feel rich in minutes now. Good. I can tell a little bit story. So in 1882 was when Klein first mentioned, what is called now the Klein bottle in one of his lectures. Here is a picture made by Bernard Boyd. I like it very much. He doesn't think it has to be ball light. Here, the picture in Klein's book, and he said, we can call it Klein 2. And later, there's a fantastic book, this is a book that was published in German by Hilbert von Bossel, and it's on geometry and imagination. And it's all, you can find it around. And it's a fantastic project to just get a few pages and read slowly, because it's pure math joy there. And they said we call this plane surface, and I don't speak German, so I'm not going to pronounce it. That is plane plus, just say. Here is another illustration. And in 52, this book was translated to English. And it had a picture of the Klein bottle, the picture that you see in the edition of 1932. And the translator saw something that was looking like a bubble. And the word surface and the word bottle are close in German, so he just wrote bottle. And I think it was an unfortunate mistake because now we associate our surface with something that looks like a ball, and it's not the right association, and I'll try to convince you about that in a second. But now, the Germans also, they call it Klein bottle, because now they don't even know that. So here I have another surface. And the question is, what is this surface? Very similar. Inside, a Klein bottle, the standard Klein bottle will look like, well, I have this, here there's see the yellow thing inside. Double Klein bottle here. Especially mathematicians, we like to be arrogant and, so it's very rare that somebody says something because maybe you're wrong and then somebody's going to look you're not, so smart. So good. So here, if I just don't have the brown part and I do this, so then it will be a standard Klein bottle. But what is this? And again, we should go back. When I ask, I claim this is a Klein bottle, by the way. And when I say a Klein bottle, we should say, what do you mean by a Klein bottle? Of course, what I mean by a Klein bottle is, you can pass this around. But what you mean by a Klein bottle is something that looks like this, the standard Klein bottle looks like, well, yeah, but if you give a precise mathematician concept of this word, that is also a Klein bottle. So this is my meaning, something that you obtain by doing this, but you have to process stuff. So let me try to convince you that it's a Klein bottle. So here I have a tube. I think, I usually like to talk to one or two people, like so big I have lost control. But here, this is a tube that is wide and it gets small. Here, it crosses itself. I don't know if you can see my finger here. And then it gets bigger and like this. So this is, Klein said, start with a tube, make it go inside, traverse itself, and then just you attach it. But when I glue these two circles together, the golden circle, that is the Klein bottle. It's a little fat here, whatever. But it's a Klein bottle. Up to the formation, like the 40 to make a Klein bottle. Now, I could also, the important thing is, remember, when I glue the two edges, I have to I have two arrows pointing in the direction of my fingers, and I have to make them match. So now if I put it inside, I'm just trying to keep my fingers set. And now my fingers are still matching, but I have the ball inside. So this is up to the formation, the same thing. Well, here I try to show you with other set of pictures. So that was also a Klein bottle. And I must say, I worked in this area of mathematics, but I discovered this by accident. I was making Klein bottles, and then I said, oh, what if I don't close it this way? And I have to think for it. I wonder, all these people that think fast, there are, but a lot of us, including some people who are, they get it, and they're living by doing and teaching math, they're not that fast. So don't feel bad about the important thing is to think and reflect and understand. Speed is not an issue. So there are many other bottles you can have. If you have an odd number of bottles, one inside the other, like, or you can't see very well, but there's three things there in the right. That's a Klein bottle. This one here, though, I don't know. This one looks very much like a Klein bottle, but in fact it's not. And the idea is, well, I'll try to explain it, fast, but if you have a tube, you pass it once, And you glue, you're going to match the arrows. And here, the two, you can see passes twice through itself. And when you pass it twice, and you can check this, the arrows are not going to match. So for the mathematician, this is, this can be deformable. If I put this, if it was a matching material, I could make it go to itself. I could pull the turquoise things out and make like a donut. And study. So it's like, even number, not, not a Möbius, not oriental, not like all number, like this. Now we have another one that looks even less Klein bubble-ish than the other one. And this one, I know many mathematicians, well, myself included, in a year, 2 years ago. But this is also a Klein bottle by my definition that I gave. And try to ease you here. Again, this is always, the question is, well, this is something that I constructed by following the instructions to, make a Klein bottle. So we start with a rectangle here, and it has edges with arrows. Now, I'm going to bend it. So here I bend, and I bend. And remember, I know by other arguments that to do the gluing, to perform the gluing, the thing has to cross itself. I know that. But maybe it crosses itself in another way. So what I'm going to do is I'm going to glue this top blue and the bottom blue across the middle light blue. So I try to make it, it's like a figure 8. There it is. And there it is. And now I have to make this bigger, but I have technical problems. But what I do is, well, I glue it like this, but if I'm going to twist it once and glue it, I managed to do my thing of, following the map. Anyway, I'm speaking fast, but this is it. So here it is. I've stole this picture from somewhere. Well, can't see, but this is like a figure 8, and there's an 8 that that have a twist. And one more Klein bottle. Here it is. And this one, well, maybe this one was discovered in a special way. Glenn Lawson, which is the mathematician whose face I put in a previous slide, he was trying to find surfaces in a certain space with a special property. And the property is they are kind of bubble soap-like. Now the bubbles, when you make bubbles, they try to organize themselves to in the smallest area, for instance, enclosing a certain volume. So here, when you screw, you get a spherical thing when you have a standard bubble. If you do that in situations that I don't have to explain, you get something that is beautiful. Here it is, and it's very hard to understand. And there it is. And this is also a Klein bottle. So now I show you a lot of things that I'm calling Klein bottle. So let's try to classify to see which sense are similar or not. So I'm going to go gently placed. The surface is a gently placed in our space. If when we place it, we don't fold. We don't fold. This is like a fold or clamp, or you have to keep a smooth thing. It may cross itself. So this is what I mean by gently placed. This one is not gently placed. So this one, by the way, this is also a Klein bottle. And this point here, there's a pinch. Have to make this better, but imagine that you have two planes of clay, like this, and then, well, I can't explain well. You have to look at the thing and see how they are connected, and the color tells you cannot make this intersection without having a pinch. So basically, just like you fold with your finger. And one way to express that, well, if you heard the word tangent plane, it's tangent plane, but if not, you think of a way that is just softly laying on the surface, only touching around the thing in one point. If I have a pinch, it's moving. Now here I have a better pinch, like you can see better. Here there's a pinch. This is a Möbius line with a pinch. So this is not gently placed. It's around. And sometimes in the surface property itself, this plane that you put softly, there's one for each, this layer, this sheet of the surface there. So here is the Möbius line. So here I have 4 different things, surfaces that I said, these are Klein bottles. And would you find a deformation, a gentle deformation between them? And I didn't read it, but a gentle deformation means like the deforming surface that at every angle you get is a gentle deformation. So there's no pinching, there's no folding, there's no crease, abrupt things. Because maybe we can deform, one pair of this. So this is one question. Anybody can? Okay. No answers. Another question is, well, because you can find maybe, well, it's, I don't know, what time is it? It's almost 5:30, we're tired. Maybe there are deformations, but we can't find them. But the question a mathematician would ask is, are there deformations between any pair of this? Maybe I can deform one into the other. And if there are, which one we can deform one into the other? Well, it turns out that these two can be deformed one into the other. And I tried to I forgot. I have one surface to show that, but I forgot it. But I'll try to explain you how. What is anybody have the Klein model that looks like this? There are not too many of these things, by the way. Okay, there it is. So here, when I'm putting my finger in this tube, where the blue arrow there is in the slide, imagine that now I put 2 fingers and 3 fingers and I expand this neck here. So I grab the neck and I expand it. This neck here. So this hole becomes, not designed to do talks with microphone. So this hole, I make it big, 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 big. So then I will be able to grab this little tube that is inside. Again, I have to make better illustration for these apologies. I can grab the tube and pull it out, and it will look like a more standard Klein bottle. You can check. So I just show you how to deform it, these two things. There's a gentle deformation. I didn't increase, I didn't do anything abrupt. And here is the big theorem. There are 3 deformation classes of Klein bottles. So anything that is obtained by the recipe I gave you for making a Klein bottle, by the map that I gave you, can be deformed in one of these things. If the standard Klein bottle is I call it the figure 8 Klein bottle, or the mirror image of this. Okay. Let's see. I'm going to show you one more thing that I really like. Maybe the cheaper, but I shouldn't have. So that it can be up.
Green, orange, and white.
Oh, there, yeah, I made it, yeah, there. No, in fact, I can't sew. This I designed it, but I can't sew. I hired a woman whose native language was not English to make this, and she said, "Your work makes me headache." Well, it makes me headache too. So this object here, what do you think it is? Yeah, it's a Möbius strip. And here you see there's one twist. So this is a Möbius strip. And I have two Möbius strips. One is the mirror image of the other. And now the boundary, as I mentioned, this edge is only one single curve, and I'm going to zip them together. So I have two Möbius bands, and I'm zipping them together or gluing them across the boundary. And I got a Klein bottle. And of course, well, the Klein bottle, you cross itself here, the zip, should traverse the piece, the tube here. But this is again a Klein bottle. So play with two Möbius bands to get a Klein bottle. Okay, so now, this is for the non-mathematicians. I mean, all these ideas, it's just, I feel like I'm cracking the door open. And I told a lot of things, and these are things that we, humanity, thought for centuries. So if you're a little lost, or you get lost and you didn't understand one piece or another, of course, it's a spectacle, and you get a glimpse of the idea. But if you really want to understand, you have to enter that room and stay there and work and work and work, and then you will have understanding. Here, I'm just encouraging people first, not to body, you don't understand some parts or any part. Second, things are understandable if you put time there. And now I'm going to use, I was faster than I thought, but I'm going to talk a tiny bit about a different topic, but everything is related, which is somebody fantastic I'm writing a book about, is Alicia Moon. Alicia Moon was a lady there. She was born in 1860. And what I haven't saying here is, what I have her saying there is a letter she wrote to another mathematician, much younger than her, but, love math has no ages. The name is Coxeter, and she said, I can tell you how thrilled I am at the thought of seeing your magic mirror. Now, Coxeter was playing also with the mirrors and the geometry. That's Coxeter head. They are trying to play with the mirrors. I don't know if you can see in the bottom right, if you play the mirrors, you get certain shapes and symmetries. And this is, what Alicia couldn't wait to see. So, as I said in the previous slide, she studied the coordinate, and it was a little bit accidental that she started to understand or heard about these ideas. In 1860, everybody had much less education than we have now. Women have, of course, even much less. And she was not rich, so she couldn't get tutors. But a friend of the family came and explained some ideas. She really enjoyed these ideas and again kept thinking about them. So the question would be, well, 4 dimensions. We have 3 dimensions, like that we are scalar, that, and maybe the height tells you how to place a point in this space. How do we think 4 if we cannot really see it? So same way that we do with the Klein bottle, that we do maps in our mind. We play and understand the space, even if we cannot really see it. But in mathematics, again, we play that game quite a bit. Okay, so here is, let's see, one thing to do. So we're going to pretend now that we are 2-dimensional beings, but we live in a flat world, and we are like circles or we're flat. And we try to understand what a square is. And how could we? Well, one thing that we can think of is slices of a square. So here I have a slice of a square that just goes parallel to the plane and slices it. So it's like a stack of little squares. And that's a cube. So, sorry, I didn't say square. We're trying to understand a cube in our two-dimensional mind. But if you accommodate the cube in a different way and you make it go through the plane, you will see different shapes. And again, the shapes, the slices are the things that you can think, because now, we're two-dimensional. And here is one more, this is even more different. So this is one way. Now, I have another slices again. Here it has, the on the left, we have this sphere crossing your flat world. It's kind of magical, of course, because you cannot go through material. But if you are a two-dimensional being, well, what you see is a circle, and what you see, like your glass, when you see some kind of shady thing that in your head you can reconstruct as a circle. Sorry, I wanted to show this again. Come on, but I have to use. Okay, got it. Sorry. I lost my mouse here, very well. There it is. I want to show you this again. So now, and this is again, first time here, third slide, here it goes. So if we have a four-dimensional sphere, whatever that means, like you have a circle, then you have the sphere, and then there's something else. But if we have this three-dimensional sphere traversing our world, there's one more direction that hard to conceive as an imaginary that says it will look like in the picture on the left, which is there's a little sphere that goes, there's very new, and then small. And this is working a little bit by analogy, but this is how we start to construct the idea of four dimensions. So Alicia, well, she had to write a book, but it was almost accidental, this again, that she had to write part of a book of her brother-in-law, the one who had taught her about dimension 4. And he said, a tetrahedron, now, a tetrahedron is this shape that you see there in red. The shape that all its faces are in equilateral triangle and there are exactly 4 and there are exactly 3 of each vertex. So it's very symmetric. I have here is the tetrahedron. And there's a lot of math here already because if I move it this way and I tell you close your eyes and I move it, you wouldn't know I moved it. So this is the shape that I can transform it and still keep the shape in many ways. If I had a mirror here and reflect it also, so a lot of symmetry, we love symmetry in math. And so now she said, well, start with a cube. This is the cube. And first we're going to choose 4 vertices. The cube has 8 vertices. We're going to choose this and this and this and this. The property of these 4 vertices is that no 2 of these vertices share an edge. Okay? If I have to go from this finger to this finger, I have to cross through 2 edges. And then she said, now you can cut off every alternate, these are the alternate corners or alternate edges. And I want to chop off that corner. So I'm going to slice like this. And I'm going to slice like this. So this little vertex is connected to 3 other vertices. I'm going to make a plane passing through these 3 vertices and chop. And then she's doing that with the 4 vertices that we choose. So nice. And then you get a tetrahedron. So this is already fantastic thing. It was known, I don't know if she knew or she discovered it. In math, we tend to pass this around. We discover and rediscover things. But then she added, okay, now, let me do something before I say this. So here, this is another map if you were a two-dimensional being, here I have another way of constructing, another way. I have a way of constructing a cube instead of construction. So here what you have to do is, well, if you cannot see, this is called the net of a cube, and the idea is the edges are colored, and I have to glue the edges that have the same color. So for instance, here I have light green, so I have to fold and glue. And fold and glue and fold and glue and fold and glue, get a cube. Of course, if you leave, can I borrow the paper? No, just like this. If you leave this in a flat place like this page, I cannot fold. I'm stuck in the two-dimensional, I can't. Of course, you could say, well, maybe I can deform it, but then they're not squared if I do like this. So here you cannot fold it. If you had one more dimension, so if you were two-dimensional, you can fold, and then you glue it. But in two-dimensional, you can only just draw the net and try to imagine how would the thing look when you fold. Well, here, I have a net. Yeah. This is the net, or the way to construct a four-dimensional cube. So here we have 8 cubes organized in a certain way, and you have to glue the faces that have the same color. And of course, I can't do it. This university, they have only 3 dimensions, but Stony Brook we can. Well, we are a public university, we barely have 3. Anyway, and now, what? Anyway, so here this is the cube. So again, if I would be able to fold, and maybe there's an image that you have seen called the tesseract, which is the four-dimensional cube with cubes inside cube. Well, this is kind of a shadow of a cube. I have this. So, but there's something called the four-dimensional cube. Now I'll go back to my story. Fine. So she said, oh, sorry again. Sorry. I'm trying to go back. Here it is. So here she said, in the same way that you did a cube and you chop alternate corners, if you do the same thing with a four-dimensional cube, you get another shape, which is cube-like in the center having those symmetries. Well, she called it tesseract, we call it now the 60 side. It's a shape made of 15 tetrahedrons organized in a certain way. And she came from there doing, fantastic things. The book was published and she kept thinking, and she rediscovered this 6 shapes. So here in water, you see there's 5 shapes. We have this property similar to the cube and the tetrahedron, which are very symmetric. Each face is a regular polygon, and they have the same number of polygons at every vertex and so on. There's another more shape, which of course is 4 dimensions. The only thing I can show is something which is we can think of as a shadow, in the same way that our 3-dimensional bodies have a 2-dimensional shape. 4-dimensional thing, hard to think that is true. They have a 3-dimensional shape, and those are there. So there are 6 things like that. She rediscovered, and she studied how they were when you intersect these shapes with spaces, what do we get? And the story goes, she did this all alone. She was raising children, not a lot of money, and by the way, she thought her husband found. They created together the Liverpool Mathematical Society, and at some point, probably that she had some contact with mathematicians, she found in a magazine a picture that was, that seemed like drawn from her models. And the picture was from a paper of Peter Schauter, who had that drawing there. And here is Alicia, that's her model. So she wrote to him, and they developed a collaboration. They published papers together, and she left us with some metaphor expansion and contraction transform these words in all dimensions. Here we see in dimension 3 some regular of these shape rods. Okay, I'm done.